Okay, let's find the global max of this function on this interval. So we have a continuous function. This is a polynomial. We know it's continuous. It's also differentiable, but it's continuous on a closed and bounded interval. We're including both endpoints, brackets, so it's closed. It's bounded because we don't have any infinities. We're guaranteed we're going to have a global max and a global min. Let's find both. Okay, so we find our critical values. How do we find our critical values? By finding where the derivative either doesn't exist or equals 0. So first we need the derivative. And we should just be able to look at that and see we get x squared minus 8x plus 15. That is a continuous function. That exists everywhere. So it does not exist. Something we're supposed to check, doesn't happen. We don't have to worry about that. Equals 0. Oh, well, now we're going to have something. X squared minus 8x plus 15 equals 0. You should immediately see that's x minus 3, x minus 5. And we get two answers, 3 and 5. Now, this is important. Look at that 3. It's not even in my interval. Who cares? Something interesting's happening at 3. Don't care for the context of this problem. 3 is not in the interval 4 to 10. So throw it away. Don't care about it. I only care about 5. So I have to check the function value at both endpoints and that one critical value that actually lived inside the interval. So I'm going to plug all 3 of these into the function, see who's the biggest and who's the smallest. And I'm going to use the calculator to do all of these. I'm going to do them in numerical order. Now, if you got to check a bunch of values, sometimes it's better to plug it here into y equals. So that was 1/3 x cubed, x yeah. Sorry, I gotta delete that. I messed up. Okay, 1/3 x cubed minus 4 x squared plus 15x. And I could graph this guy if I wanted to. Can't really see anything happening at any of those points. Maybe I could change my window if I wanted to. Really only care about 4 to 10, so might as well go ahead and just graph 4 to 10. Oh, it's so big I can't see any of it. See, I could sit here and I could play around here. Maybe negative 100 to 100. See, I'm kind of wasting time here. It'd been easier just plug all these in. I'm just showing you could. I wasn't getting anything. I'm like, what is going on? I typed that wrong right here. Right here, I need to insert that minus right there. Okay. See, now, even if I go zoom standard, zoom back to standard, yeah, I can see some stuff. See, my point is, yeah, I could play around with the graph and try to figure these out. Or I could go right here to a value. See calc right there above trace, second calc. Number 1 value, I can just plug in these x values. 4, I get 17.3-ish. at 5. Now, watch, all I gotta do is just type 5. That's all I typed. 16.67. And then 10. Again, all I'm doing is typing 10, 83. Point whatever it was. 33. Oops. There's my max. It's my global max. Globals can occur at endpoints, locals can occur at endpoints or at points in the middle. This is, it happens to be a local max. We would need second derivative test to prove that. But he's also the global max, or global min. Sorry, that's a min. Because that's the smallest number. Okay, I think that's a good place to stop. So when you're looking for globals, or also called absolute max or min, on a closed interval, find all the critical values, and then you have to check in the original function all your critical values and your endpoints. Whoever's the biggest is the biggest, whoever's the smallest is the smallest.